So let's move to chapter 14, which is very confusing. Systems of particles. Okay, systems of particles. This means generally when we have many particles, force maybe Fj, and there is internal force each other, and we would like to know how this one move. For example, okay. That's our attempt. And the textbook explains this concept rather, explains almost everything. But often it is too much. So I will explain the basic concept of systems of particles dynamics by just introducing using two particles. Because if you understand what's going to happen in two particles, then you can understand what's going to happen in many particles. So start with the simplest case. Suppose I have two masses linked by rigid but massless link. This is rigid but massless link. Very strange link. Or also I can say the mass of this link is very, very small compared with this mass. And I have mass 1 and mass 2. Okay, suppose this mass experience the force, external force acting on the mass. And suppose this one experience another external force. And I want to know how those two masses move. Okay. Then I can write, maybe it may move maybe, right? But Newton's second law says if one particle, certain particle, experience some external force, then the resulting force induces the mass to move, not the two particles, right? So I have to apply Newton's second law on each particle, right? Momentum case, we say the momentum of the whole system already. Well, but we didn't say anything about the Newton's second law for many particles. That's important. So we have to apply Newton's second law for each particle. So let's apply on each particle. So what I have to do is I have to draw the particle. First step, I have to find out all the forces. That is F1. And there should be some force induced by the particle 2 to particle 1. So I draw 1, 2. That means the force due to the particle 2, internal force. And I use a small f to indicate that this is internal force. Okay, that has to be equal to ma1. And this has to be vector and vector. And another equation, pictorial equation of motion would be, there is a particle 2, m2, and external force is F2, and internal force, this is F21 vector. You can do it, right? And that has to be balanced by ma2 vector. Okay? Yeah, we just use the Newton's second law for each particle. Now, let me write down this graphical equation in terms of the coordinate I select or in vector form. Then I can write simply F1 plus F12 is equal to ma1, and F2 external force F21 equal to ma2. Right? And note immediately that F12 is equal to minus F21 because it is internal force. Because Newton's third law, action and reaction. Okay? Therefore, I can write F1 vector plus F2 vector is equal to, M1, M2, M1 A1 vector plus M2 A2 vector. Okay, we do know what is this. This is a total external vector. And what is this? How this is related with M1 V1 and M2 V2, and how this is related with M1 R1 plus M2 R2 vector. What I'm saying is we understand this. And we wrote down this mathematically, but we cannot visualize what it means physically. Then I do not know this, what about this, and what about that? That's my way of thinking. And I still cannot understand what it is. Then what you can do. Let's see this for a very simple case. So to understand this stuff, If I understand this, then I can understand that, then I can understand that. Therefore, let's try to understand this by introducing the simplest case. Okay, suppose I have two mass. And this is moving with this direction only. Okay, then m1 x1 plus m2 x2 is related with plus m1 plus m2 x something. What is that? That is, anybody can remember? We define that x bar is equal to x1, m1 x1, m2 x2, m1 plus m2. What it means? m1 plus m2 is a total mass. And x bar. That means the position as if the total mass is located. What is this? Huh? Center of mass. Center of mass. Okay? Wow, that's interesting. So normally in this lecture I use this xg. Therefore, this is, according to the observation from one-dimensional case, I can write this is m1 plus m2 rg. Rg is a position vector of a center of mass. Okay? Then, taking a derivative of this with respect to time will give this. Therefore, this is equivalent with the velocity of a center of mass, because I'm taking a derivative with respect to time over this expression. And this is equal to m1 plus m2 . Therefore, this means that if I expand this idea in three-dimensional, then I can say if I have many forces acting on many particles, then I can still say that m total, summation of all mass, multiplied by acceleration of a center of mass.